All right, so the second model that we're going to use to understand molecules is molecular orbital theory. Okay, so we touched on this in Chem 2 a little bit, not much, and we're not going to touch on it a whole lot here, but it gives some valuable insight into how molecules are, and so we need it. All right, so molecular orbital theory, which we oftentimes just call as MO theory. All right, so in valence bond theory, we considered bonds to be the overlap of valence electrons, right? And so we sort of thought about bonds as being the electrons being right in between two nuclei, and they spend most of the time between them. In molecular orbital theory, it's a little bit different. In molecular orbital theory, we consider atomic orbitals. Remember, we did the electron energy diagrams like this, orbital energy diagrams like this. Remember that? So here's one hydrogen atom. Here's another hydrogen atom, right? So in molecular orbital theory, we consider the mixing of those wave functions, right? So if we take two atomic orbitals, 1 and 2, here's one hydrogen atom, here's the other one, and we mix them, we get a bonding molecular orbital and an anti-bonding molecular orbital, okay? And by the way, their shapes are depicted right here. We don't need that a whole lot right now, but it's valuable to know what they are, okay? So the bonding molecular orbital is lower in energy than the two atomic orbitals. And I'm going to use this term a lot. I'm going to call some of your attention to it. We say that a molecular, just a second here. We say that a molecular orbital comes from a linear combination of atomic orbitals, okay? And what that means is if we take two atomic orbitals and we mix them, they convert to two molecular orbitals, okay? So, and look what I have here. I've got an atomic orbital here, an atomic orbital here. When we mix those orbitals, really the wave functions, okay, we get a bonding molecular orbital and an anti-bonding molecular orbital. Now you can see that the bonding molecular orbital here has electrons in it. The anti-bonding doesn't have anything in it, so it's sort of like it's not there. Okay? So the bond is actually this. Now here's an important difference. The molecular orbitals, that is the bonds, they extend over the entire molecule. Alright? That's a little bit weird. Okay, we're not going to make much out of that, but it's an important difference. Okay? Now molecular orbitals are a more complete analysis of bonds because they include more things that we're going to need later. Okay? Both constructive and destructive interference. Here's our destructive interference. Here's our constructive interference. And also, as I said here, the number of molecular orbitals created must equal the number of atomic orbitals that were used. All right. Now, note here, as I said before, the anti-bonding molecular orbital has a higher energy than the atomic orbitals. All right. It's empty, so it doesn't matter. But if we had electrons in it, it would matter. It'd be high. It would be expensive. Okay. And the bonding has lower energy than the atomic orbitals. Okay. So, and let me just read that last statement. When the atomic orbitals overlap, the electrons go into a bonding molecular orbital rather than the anti-bonding molecular orbital in order to achieve a lower energy state. Of course, right? That was the Aufbau principle, where electrons go into the lowest available energy level. Okay, and that's about all we need with respect to molecular orbital theory for now.